Well, ladies and gentlemen, we're looking to the second session now, and what we're going to do here is actually in some way take you to the International Space Station. Yes, you're going to ask that question, what the heck has space station got to do with the minerals industry? Well, we're about to find out. Our guest speaker here today is Dr. Robert Greene, Director Micro Devices Lab at NASA, the National Aeronautics and Space Administration. His topic is mapping the minerals of the Earth's arid land regions with NASA's Earth Surface Mineral Dust Source Investigation, known as EMIT, on the International Space Station. For me, the short version of this is NASA is watching. So look up and smile. Ladies and gentlemen, would you please welcome Dr. Robert Greene. Robert. Not yet.
How are we doing? Testing, perfect. Okay, it's absolutely wonderful to be here. I must admit, long ago, 35 years ago, I was a geologist. I worked for Molycorp, which had a rare earth mine, Mountain Pass in California. Then I worked with Unocal Oil and Gas, so I do have a connection, but it's 35 years ago. 35 years ago, I came to NASA to pursue a new technology which allows us to map molecules without touching them. It's called imaging spectroscopy. So I moved to the Jet Propulsion Laboratory, and I want to tell you about a mission that is now on the International Space Station and mapping the minerals of this planet, and those data will be available to those here, and I think there are possibilities for amazing disruption with the coverage, the uniform coverage of our planet that we will get from EMIT. So let me continue. So again, this is the concept. We have an Earth, and we want to peel back and map the minerals on the surface of the Earth, and we're going to use a technology called imaging spectroscopy, which is very, very disruptive. I'll say a little bit by way of introduction. I and some science colleagues in 2016 wrote the proposal to NASA for this investigation. We were selected in 2018 to build the instrument and launch it, and it launched in 2022. So how do we look at minerals? By getting further away from them. That seems counterintuitive. It turns out that minerals are molecules, particles, and they interact with light differently based on their composition. So just like that carpet is green because it's a different molecule. This is the spectral range from 400 to 2500 nanometers. Our eyes just see this little piece of it, and we only see it with 3 detectors, blue, green, and red. But if you measure the whole spectrum, you can see that different minerals, their names are up there, have different fingerprints. So they have different unique spectral signatures. I've included some more typical surface minerals, but also this mineral is the mineral bastnasite. It's a rare earth element-bearing mineral. It has a spectacular spectral fingerprint, so you could look for rare earths. And this mineral, this green one, is the mineral hectorite. It's a lithium-bearing mineral. So there's leverage for looking at minerals on the surface of the Earth through their spectral signatures. And so that's the technology that we've taken to the space station, is looking at the Earth with an imaging spectrometer. So the approach we have, we built an instrument that looks down, in this case from the space station. It looks down at a cross-track swath of the surface of the Earth. We send that light, it comes from the sun in our case, to a telescope, to a spectrometer, to a detector array. Every column of that detector array is measuring a spectrum from 400 to 2500. So we move across the Earth, we measure the spectra, we get image cubes. So now we have an image of the Earth, but for every point, instead of just 3 colors, we have 285 colors with all the leverage of that spectral signature to map the minerals. And we can go directly from those measurements through calibration to mineral maps based on their spectral signatures. Now, just by way of comparison, when I was in graduate school, I would go to the laboratory to measure a spectrum, and it would take me 10 minutes. This instrument has 1,240 spectrometers, and it measures a spectrum 250 times a second. So we're collecting 300,000 spectra a second compared to my 10 minutes in graduate school. So that's the technology. That's what's disruptive and this is state-of-the-art in the 21st century. So what does it look like to build a NASA instrument? This is a glimpse. This is what the optics do. We've got a 2-mirror telescope into a spectrometer, so we take white light in the front. We make the spectrometer. We use state-of-the-art components, some of which are built at the Micro Devices Lab, which I'm the director for at the Jet Propulsion Laboratory. There's the spectrometer. There's it being aligned. There's a CAD model of its configuration. There's the team in the clean room. We built it in a clean room because it must have no contamination. And there it is sitting at the Jet Propulsion Laboratory about March of 2022. And again, that took 41 months, and we did it through COVID. It's very hard to build things in COVID when you have to not be near other people, but we managed to navigate that. It took us just a little bit longer. And then I was very fortunate. Not all rocket launches are successful. I've been to some that haven't. But on the 14th of July, 2022, on a SpaceX rocket from Florida, we launched the space station. So there you're seeing the launch. We're the large white box. There's the dock to the space station. There we are celebrating the launch. And there's a picture from an astronaut on the space station, and I've labeled Emit, looking down at the Earth, and the robotic arm was used to install us. And at the end of this, if there's time, I'll show a movie of the launch and the installation. So how is it working? It's working very well. We launched the 14th. We turned on the 28th of July. On the 28th of July, we came in over Perth, Western Australia, as a good place for minerals. And we got spectra immediately. I don't have those up here. But then we went into full operational cadence. So each one of these is an orbit chunk over a chunk of the arid land portion of our planet. And this is phase 1 observations. You'll see we visited all 6 continents except for Antarctica. The space station doesn't reach those. And we're mostly looking at the arid land regions because my science here for NASA is to look at the composition of the dust sources. Dust interacts with your system. It has a major impact here in Saudi Arabia in the Middle East. It can be a human hazard. It also heats and cools our planet. So that's why we're looking at the arid land regions. For my investigation, but for you and for minerals, we can map hundreds of minerals, and we can map them uniformly for the entire planet. So there will be new geological maps for planet Earth that will be based on these spectroscopic signatures that I believe will become available in the next year. And I think that can be disruptive because it will put all the mines from arid land regions in context of a base map that is the same everywhere on planet Earth. And that will open opportunities for artificial intelligence, machine learning, to look for new innovative ways with this. Really, it's geochemistry of the Earth's surface we're getting these geological maps via spectroscopy. And this is a very special cube. This cube was one of the first ones we looked at. It's in the Arabian Peninsula. I was invited to come to this conference, and I said, well, I should see where that is. This is about 100 kilometers from Riyadh. So tomorrow, after the conference, I'm going to go do some ground truth. And we've made predictions based on spectroscopy, what minerals we will find, and we're going to check to see if those are there. I'm quite confident. And this is that cube now being blown up. There's the cube. We've got a spectrum. There's the mineral maps of the ones that I must map. I'm looking at iron oxides, the grain side, as well as carbonates, sulfates, various micas, various clays. That's the data we measure, radiance, the full Earth system. These are the spectral signatures for those 2 places. And there is the signature of kaolinite. There's the carbonate. Here's the hematite. Here's the goethite. And again, a vast majority of minerals have unique spectral signatures. So I'm just showing a handful here to demonstrate the concept, but you can take this to hundreds of minerals. We've mapped hundreds of minerals on the Earth with airborne spectrometers, but this is the first one of this quality in space. And just to take you around the world from Emit, this is maps of minerals in South America. This is in Chile in the arid land regions. Here we're looking at gypsum, dolomite, the carbonates, montmorillonite, and different combinations, all of which are just mapped beautifully. And so this is an extraordinary, how do you map minerals? You get further away from them and put your instrument on the space station. And I'm just so excited that it's working just as we planned, in fact, a little bit better. And then moving around the world, this is the Western United States, that's Lake Mead, more mineral maps by measuring the spectrum for every point in that image. at the rate of 300,000 spectra a second. And I'll just off-world, we take this technology with NASA to Mars and to the moon, and we're building a spectrometer right now which will go to Europa, one of the moons around Jupiter, to look at questions of habitability for possible life. So again, moving on here, I was told to keep it not too long, so there'll be time for questions if there are any. But my objective, what I proposed to NASA, and they gave me $100 million to do it, was to answer these science questions related to dust. There you can see dust leaving the surface of the Earth. Those are the arid lands we're going to map with EMIT. All those data will be available through NASA's open data policy, so all of you have access to those. We have the spectral signatures. We're now on the ISS mapping. We launched successfully. That's our first light near Perth and our first spectra. We've got this much coverage. We're mapping the minerals. We're going to achieve my objectives, which is my contract with NASA, which funded me the money. But the data are going to be available for everyone, all our colleagues here from all the countries of the world, through the NASA open data policy. And here's the area. We expect to have this area covered by the end of 2023. And we will have multiple coverages, because even today, in a place like Saudi Arabia, it's cloudy. So this isn't a perfect day to map the minerals of Saudi Arabia. But we will have maybe 10 observations to look in this area. So we'll pick the good ones to do the mineral map. So this is the area for which there will be a uniform mineral map available for this part of the world towards the end of 2023. All these measurements are available from what's called the Land Processes DAC. You can Google that. I don't have the QR code up here. Now I want to take you a little bit further. Again, we're looking at molecules. Minerals are molecules. But there's some other interesting molecules that we've learned we can see that have some relevance as well. So very soon on, when we looked at the EMIT spectral signature, we looked in a part of the spectrum towards 2 microns, and we saw these phenomena. These are plumes of greenhouse gases leaving the surface of the Earth for various reasons. Up there are methane plumes in Tajikistan, and those are super emitters near the Caspian Sea. There are leaks. For some reason, that methane is going straight into the atmosphere. It's not being captured. It's not being sold. And as a greenhouse gas, which is relevant to the nature, the trajectory of our planet, finding super emitters, helping people clean them up, is something that EMIT will be able to contribute to from the International Space Station. We also see carbon dioxide. These are carbon dioxide plumes coming from 2 large power plants in China. So that's something I'm excited about. It's a spin-off benefit because we're using spectroscopy to map molecules. Minerals are molecules, but so is methane, so is carbon dioxide. So we're going to map those molecules too. And then what's quite interesting, EMIT was off for a little while they fixed something on the space station, but we turned back on, and these measurements were collected near Cape Town, South Africa on the 7th of January, 2023, last week. So we collected these measurements near Cape Town. Those are the data, those are the spectral signatures, those are the mineral maps. So this is a disruptive technology where you can map hundreds of square kilometers with seconds of data within 24 hours, and then I will argue with machine learning, AI, there's tremendous potential for mineral exploration with this new technology called imaging spectroscopy. And this is what's up for us for the next 2 weeks. This is the plan for the data sets. EMIT will measure from the 11th of January to the 25th of January. They will continue through the whole year, but you can see we're going to visit, really, we won't quite get to Europe, but 5 of the 6 continents, and we're going to continue that through the year. So there'll be a huge data set of minerals and spectroscopy and retrievals that we can use for a whole host of scientific questions, which is my responsibility, but I think in the mineral business, I can think of ways where this could be very disruptive. It'll be a new base map of geochemistry via spectroscopy for our planet. And there's a thank you. There's a picture of EMIT. It's quite remarkable. I'm very fortunate to be in this position. That's the arm that installed EMIT. So I have a few minutes for questions, but while I listen, if there are any, I'm going to show a video of the launch and the installation of EMIT, which is quite extraordinary and gets me choked up when I see it. So if we could start the video, that will give people of how I spent my summer of 2022.
We're going to start the video. Am I that close?
It does not have sound.
How
are we doing on time?
There? We've got a couple of minutes. While we're waiting for that, if
There we
it
go.
pops up now, let's look at it.
All right, so this was...
0.
There's the SpaceX taking off, heading to the space station. I was there with my family. There it goes. We watched the booster separate, come back to Earth. It landed. There's the booster separating. That's going back to Earth to be reused. We saw a few of those. There's the second stage taking us on with the capsule. There goes the booster back to Earth. Then the second stage left, and now we're going in the Dragon capsule. This is called the trunk. That was a mitt in the back. Here's the capsule coming to the space station. This is now a camera view from the space station looking at the Dragon, SpaceX Dragon. There we are coming in to dock. They've opened the nose, and this is the docking of SpaceX CRS-25 was the name of the mission, the 25th mission. And there's the connection to the space station. Now, it's quite tricky. Our instrument is in the back of that capsule, so they have to use the robotic arm to grab, emit. There's the instrument being grabbed by the robotic arm. It needs to be taken out of the back of the capsule, out of the trunk, moved to the place it's going to be installed. So this is where it spent the night as we waited 2 days to get the instrument, which has that silver panel to reject heat. Here it is being installed on the International Space Station. Or moving further along. I guess they passed it off to another arm. There it is being plugged in on the space station. Fortunately, they kept it pointing down. That was one requirement. And there it is installed. And then I think there's a few of its first images. So power one successful, functional test successful. Then there was light coming in over Gillamar State Forest in Western Australia near Perth. First spectra, just what we were expecting. Maps of minerals on planet Earth. This is central Algeria. Here's the site near Riyadh. Maps of minerals near Riyadh. And this is the beginning. So I think that's what I wanted to conclude with. There's the team. There's our logo. You can find us on the web. It's a great pleasure to be here and share this exciting news with all of you.
Okay. Rob, thank you for that. I have one question. We've got time for one question. Rob, you mentioned something that's very, very important to the future of the mining industry, and that is artificial intelligence and machine learning. I can't tell you how important that is and how it's impacting productivity today. You mentioned it, but how might artificial intelligence and machine learning be used for exploration of EMIT data sets on our planet?
So that's a great question, and what I would say is we know where there are successful mines all over the planet in these arid land regions. So you know what the mineral signatures associated with those successful mines are. Then you have this data set from EMIT everywhere else for those same minerals. So you can ask the machine learning artificial intelligence, are there places that look like the mineralogy of a successful mine somewhere else? And might you want to not take a look at that area? So that's just a very simple. And we actually use machine learning in the processing, but that would be just one example where you might use machine learning, artificial intelligence.
Okay, so if you're an explorer, the first thing you've got to do is get onto that NASA website, and you'll know where to look and why, won't you? Ladies and gentlemen, sorry, Rob.
I would say, and there's a new term. There's terabytes. What comes after terabytes? Petabytes. It's 1,000 terabytes. So get used to big data sets.
Yes, that's our biggest problem in the industry, data sets, I believe. Okay, ladies and gentlemen, would you please join me in thanking Rob Greene for what was a fascinating visit to space and the space station. Now, Rob's going to stay with us, and we're going to put our other panel here right now. We've got some chairs coming up.